The world of data is changing. We are no longer dealing with simple ledger entries, but with the complexity of human thought, images, and spoken word. To manage this new world, a new kind of tool was introduced known as a vector database. A vector database is a highly specialized, cut-edge system designed not to store words or numbers directly, but to store the meaning of those words and images. It is the essential engine that powers almost every intelligent AI application you interact with today. To understand this database, we must first understand its core currency, vectors and embeddings. Think of vector as a precise set of coordinates, like a longitude and latitude, but existing in a vast space with hundreds or even thousands of dimensions. We can call this the thought space. A vector is simply a long list of numbers. To capture the meaning mathematically, we use something called vector embedding. An advanced AI model or an embedding model takes any piece of unstructured data, a picture of a cat or sentence, for example, the sunset over the horizon, or an audio clip, and translates it into one of these numerical vectors. This translation is done strategically. The model ensures that pieces of data that are conceptually similar or share the same semantic meaning are translated into vectors that land very close together in the thought space. For example, the vector for the concept car and the vector for the concept automobile might be right next to each other. The vector for bicycle would be near them, while the vector for banana would be far away. The vector database is a highly efficient library built specifically to house, manage, and instantly search through these numerical representations of meaning. Traditional databases were perfectly suited for the 20th century, but they failed the needs of the AI era. Systems like SQL are fantastic at finding an exact match, like if you want to find the customer ID with, let's say, the number 402, you can easily find that. But they are deaf to meaning. If you search for, tell me about a fluffy animal that barks, a traditional system would fail unless the exact words, fluffy or animal or bark, were present. It does not know that fluffy dog is the right answer. Most of the data created today, like photos, videos, articles, is unstructured. AI needs to understand the content of a photo, not just its file name. The vector database provides the ability to perform semantic search, which is searching for information based on intent and meaning, overcoming the limitations of keyword matching. So the power of a vector database comes from its specialized internal engine, which is focused on speed and proximity. So the raw data is transformed into a vector by the embedding model. The database saves two things for every piece of data. First is the complex vector embedding itself, and second is the simple metadata, which is the key information associated with the vector, like the original text, the source URL, the date, etc. Storing a billion vectors is one thing. Finding the closest one in a fraction of a second is another. A direct point-to-point comparison is impossible at scale. This is solved by approximate nearest neighbor search algorithms, the database's secret weapon. The most common and robust algorithm is hierarchical navigable small worlds, or HNSW. Think of HNSW as creating a multi-layered map of the thought space. So we have two kinds of layers. First is the top layers and second is the bottom layers. For now, let's say the top layers can be called the highways. These layers have few connections, but they let you take long, quick jumps across the space. If you are looking for information on space travel, this layer lets you rapidly skip over everything related to cooking or gardening to get to the right general idea. And the second one are the bottom layers. Let's call these the local streets. These layers are dense with connections. Once the highway gets you close, you drop down to this layer to perform a detailed, fine-tuned search to find the absolute closest neighbors to your query. This ingenious indexing structure makes the search time incredibly fast, making real-time, meaningful queries over vast amounts of data possible. So when you ask a question or input data into an AI system, your input is immediately turned into a query vector or a set of coordinates by the same embedding model. The database's HNSW index efficiently navigates the thought space to find the k data vectors that are mathematically closest to your query vector. The distance or similarity is calculated using metrics like cosine similarity, which is basically measuring the angle between the vectors. The database does not return numbers, it retrieves the metadata associated with those closest vectors, like the actual document, image file, or text paragraph. You receive the data most relevant to your meaning, not just your keywords. The vector database is the infrastructure that fueled the breakthrough of large language models and multimodal AI. Vector databases are essential for Retrieval-Augmented Generation, also known as RAG, a technique that solves the critical problems of AI. LLMs sometimes make up facts. The vector database acts as the factual, verifiable knowledge base. When a question is asked, the system first retrieves the most accurate supporting documents from the database using semantic search and hands them to the LLM, forcing the AI to generate an answer grounded in truth. LLMs are trained on old data. The vector database provides the LLM with live, up-to-date information instantly, without the costly need to retrain the entire model. It gives the AI something called long-term memory. Since a photo, a paragraph, and a voice clip can all be reduced to a vector, they can all be stored and queried in the same database. This enables revolutionary features like cross-model search. Basically, you can search a library of images using a natural language sentence, like find a picture of a golden retriever playing fetch in a snowy park. And secondly are advanced recommendations. So recommendation systems can now match a user's taste, basically captured in a vector, against the content of products, creating much more relevant suggestions. In summary, the vector database is the invisible, high-speed warehouse that stores the meaning of the world's data, making it instantaneously accessible to AI and transforming the way machines learn, understand, and communicate. So what is a vector? Vectors in general are mathematical objects with both magnitude and direction. They are used in various fields from physics to machine learning and can be categorized in different ways. So there are several vectors by properties. These classifications are based on vectors' relationship to other vectors or its inherent characteristics. So first we have the zero vector. So this is a vector with a magnitude of 0. It has no specific direction and is denoted by 0. Then we have the unit vector, a vector with a magnitude of exactly 1. Unit vectors are used to specify a direction without a magnitude. The most common unit vectors are I, j, and k for the x, y, and z axes in a Cartesian coordinate system. A position vector. So this is a vector that represents the position of a point in space relative to an arbitrary origin. It's often used to track the location of an object. Then we have equal vectors. Two or more vectors are equal if they have the same magnitude and the same direction. So what's a negative vector? A vector with the same magnitude as a given vector, but pointing in the exact opposite direction. Then, collinear vectors. Vectors that lie along the same line or are parallel to each other, regardless of their direction or magnitude. Coplanar vectors. So these are vectors that lie on the same plane. Co-initial vectors. Vectors that have the same starting point. So, in computer science and machine learning, vectors are used to represent data. The type of vector is often defined by the nature of the data it represents. First, let's talk about feature vector. So what is a feature vector? This is the most common type of vector. A feature vector is a list of numerical features that describe an object or an event. A feature vector is a handcrafted representation of an object's quantifiable, explicit characteristics. Each dimension in the vector corresponds to a specific understandable attribute. Like in a data set of houses, a feature vector might include the number of bedrooms, square footage, and age. These vectors are created through a process called feature engineering, which relies on domain knowledge to select and define the most relevant attributes for a given task. They are often sparse and high-dimensional, and their meaning is directly interpretable. So their purpose is to convert real-world data into a format a machine learning model can understand. For example, for a house, the feature vector might be 3, 1800, 2010, where the numbers represent the number of bedrooms, square footage, and the year it was built in, respectively. So now let's talk about what are sparse versus dense vectors. So this classification describes the distribution of non-zero values within a vector, which has major implications for storage and computation. So first, what is a sparse vector? So this is a vector where most of the elements are zero. They are often used to represent data where only a few features are relevant at any given time, like one hot encoded categorical data or text data using a bag of words model. Storing these efficiently means only saving the non-zero values and their indices. So what are they basically? These are high-dimensional vectors where most of the values are zero. They are typically generated using traditional information retrieval techniques like TF-IDF, which stands for Term Frequency Inverse Document Frequency, or BM25, which stands for Best Matching 25. Each dimension in a sparse vector often corresponds to a specific keyword or term in a predefined vocabulary. And you might ask what they are used for. So in hybrid search, sparse vectors are used for the keyword search part. They excel at finding exact or near exact matches for specific terms, which is crucial for things like product names, technical codes, or legal documents. For example, a sparse vector search for iPhone 15 Pro would prioritize documents that contain that exact phrase, even if other documents are semantically about smartphones. For example, one hot encoding for the word cat in a vocabulary of 10,000 words would be a vector of 10,000 numbers with a 1 at the index for cat and 0 everywhere else. Then let's talk about dense vectors. So this is a vector where most or all of the elements are non-zero. They are information rich because every value in the vector contributes to the overall representation. These are the embeddings you hear about most often. They are dense, low-dimensional vectors generated by machine learning models, like large language models or transformer models, to capture the semantic meaning or contextual relationships of data. And again, you might ask what these are used for. In hybrid search, dense vectors are used for the semantic search part. They find results that are conceptually similar to your query, even if they don't share any of the same keywords. For example, a dense vector search for how to make a cake could find a recipe titled "A Delicious Sponge Dessert Tutorial." And in general, you might ask for an example. So an embedding is a prime example of a dense vector. So moving on, a hybrid search works by running both a semantic search and a keyword search simultaneously. The results from both methods are then combined and re-ranked, often using an algorithm called reciprocal rank fusion, or RRF, to provide a final, highly relevant list of results that balances both semantic understanding and keyword specificity. So, what is an embedding? An embedding is a type of dense vector that has been learned by a neural network. It's a powerful way to represent complex, non-numeric data in a lower dimensional space. An embedding vector is a learned, dense representation generated automatically by a machine learning model, typically a neural network. Instead of being explicitly defined, the model learns to map data, like words, images, or entire documents, into a lower dimensional vector space. The key is that this process captures latent, abstract relationships and semantic similarities between data points. For example, in a word embedding, the vector for king and queen would be close to each other in the vector space because the model has learned their similar context and meaning from a large body of text. Unlike feature vectors, individual dimensions in an embedding vector generally lack a clear, human interpretable meaning. And the purpose is to capture the semantic and contextual relationships between data points. So let's have a look at some examples. So we can think of word embeddings. So these vectors represent words. Words with similar meanings or contexts like king and queen will have vectors that are close to each other in the vector space. A classic example is the vector operation vector king minus vector man plus vector women, which results in a vector very close to the vector queen. Then we can have image embeddings. So these vectors represent images. Images with similar content, example, two different pictures of a dog, will be close together in the embedding space. And then we have other kinds of embeddings, like for user IDs, movies, genes, and more, all designed to capture underlying relationships within the data. An embedding is a technique used in machine learning to represent unstructured data such as text, images, audio, or video as numerical vectors or a list of numbers. The goal is to map high-dimensional, complex data into a much lower dimensional continuous vector space where objects with similar meanings, content, or characteristics are placed closer together. Vector embeddings are a way for computers to understand the meaning of things, not just the words or letters themselves. Think of it like giving a computer a mental map where similar concepts are placed close together. For example, a traditional search for wine for seafood might not find an article about a wine that's good with fish because the words don't match exactly. But a search using a vector embeddings would understand that seafood and fish are related and that good with and for means the same thing in this context. What are vector embeddings? A vector embedding is a list of numbers that basically represents a piece of data like a word, a sentence, an image, or a song. These numbers are carefully chosen so that data with similar meanings or features have similar looking lists of numbers. Imagine you could plot words on a graph. Dog and cat would be close to each other, but far away from computer and car. This is what vector embeddings do, but in a much more complex space with hundreds or thousands of dimensions. The magic of these numbers is that they capture relationships. For example, the famous equation king minus man plus women equals queen shows that the difference between the vectors for king and man, which represents the concept of royalty, can be applied to the vector for women, to get a new vector that's very close to the one for queen. This proves the system to truly understand the relationship between these words. So how vector search basically works? Vector search is the process of finding data by its meaning using vector embeddings. Here's a simple breakdown of how it works. A special program or a machine learning model takes each item of data, like an article, image, or product description, and turns it into a vector or a list of numbers. This is called vectorization. Then all these vectors are stored in a special database called a vector database. When you type a query like fruits, the same program turns your query into a vector. The database then quickly compares your query's vector to all others to find the ones that are closest. The closer the vectors are, the more similar their meanings are. The quality of the search results depends on the quality of the model used to create the vectors. These models have evolved over time, from older ones like Word2Vec to more advanced transformer models like BERT that are better at understanding the context of words. Vector embeddings can be created for all sorts of data, not just text. They are used for images to find similar images based on their content, not just their file names. Or audio to identify a song from just a short snippet, even with background noise. Or even products to recommend items that are similar to what you have already bought. So now let's have a look at vectors versus embeddings. The core difference is that a vector is the data structure or a list of numbers, and an embedding is the meaningful representation created by a model which happens to be stored as a vector. A vector is simply an ordered list of numbers. In computing and mathematics, a vector is a fundamental data structure, typically represented as an array or list of floating point numbers. It is the container or the format used to store data points in a high-dimensional space. Think of a vector as the coordinates on a map. A simple 2D map uses two numbers, latitude and longitude, like 40.71, negative 74.01 for New York. A vector used in a database will have hundreds or thousands of dimensions, but the principle is the same. It's just a set of coordinates. The vector database is named for its ability to efficiently store, index, and search these lists of numbers. An embedding is the result of a machine learning process that transforms complex, non-numerical data like text, images, or audio into a vector. An embedding is a vector that captures the semantic meaning or essential characteristics of the original data. It is the meaningful object. It's generated by an embedding model and engineered so that data points that are conceptually similar are mapped to vectors that are numerically close to each other in the vector space. If a vector is just the coordinates of a city, the embedding is the coordinates that were chosen to group similar things. In an embedding space, the vector for New York City might be closer to the vector for Los Angeles than it is to the vector for the color blue, because the two cities are semantically similar concepts, which are large US cities. When you perform a similarity search in a vector database, you are comparing the distances between embedding vectors to find the most relevant results. So think of it as a process. First, we have a raw data, like the cat sat on the mat. We give it to an embedding model. We eventually get embeddings. So these are basically the resulting list of numbers that capture the meaning. And finally, we have our vector, the structure where the embedding is stored and searched in the database. A dimensional space refers to the number of dimensions or features used to represent data points, like words or images in an embedding vector. The choice between a low-dimensional and high-dimensional space for these embeddings is a critical design decision in machine learning that involves a trade-off between accuracy and performance. First, let's talk about high-dimensional embedding space. High-dimensional embedding spaces for embeddings are used to capture fine-grained details and subtle nuances in the data. For example, a high-dimensional word embedding can better distinguish between synonyms like happy and joyful based on their specific contexts. Now the pros would be, first of all, higher accuracy. It can capture more complex patterns and relationships, leading to more accurate results in tasks like semantic search and classification. Other would be rich representation. It preserves more information from the original data, such as texture and color in images. However, the cons would be, first of all, the computational cost. It requires more memory and processing power for storage, calculation, and retrieval, which can lead to higher latency and slower performance. Obviously, we can't neglect the curse of dimensionality. The data becomes sparse, making distance metrics less reliable for finding true nearest neighbors. Then we have the overfitting risk. The model may learn to fit to noise in the training data, hurting its ability to generalize to new data. Now let's talk about low-dimensional embedding space. Low-dimensional spaces for embeddings are a compressed representation of the data. They are computationally efficient and easier to work with, making them ideal for systems where speed and resource constraints are a priority. The first pro for this would be the computational efficiency. It requires less memory and allows for faster similarity calculations, which is crucial for real-time applications like recommendation systems or chatbots. It has better generalization. It can reduce the risk of overfitting by simplifying the data and removing noise. The con, however, would be the loss of information. So aggressive dimensionality reduction may discard important details, potentially leading to a decrease in accuracy. Secondly, it is less nuance. It may not be able to capture subtle differences between data points. So moving on, the optimal number of dimensions for a vector embedding depends on the specific use case. For applications where precision is paramount, such as medical image analysis or legal document search, a high-dimensional space is often preferred. Conversely, for latency-sensitive applications or systems with limited computational resources, a low-dimensional space is a better choice. The goal is to find a balance where the dimensionality is high enough to capture the necessary information, but low enough to be efficient. So what is the curse of dimensionality? Let's have a look at it. So the curse of dimensionality is a term coined by Richard Bellman to describe the various problems that arise when working with high-dimensional data. Our human intuition, which is based on a 3D world, often fails in these spaces. First, let's talk about data sparsity. As the number of dimensions increases, the volume of the space grows exponentially. This causes the data points to become extremely sparse, meaning they are very far apart from each other. An algorithm that needs to find patterns by looking at neighboring data points will struggle because there are very few true neighbors. So the distance metrics fail. In high dimensions, the distance between any two data points tends to converge, meaning they all seem to be roughly the same distance from each other. This makes distance-based algorithms like k-nearest neighbors much less effective. We have increased computational cost. More dimensions mean more calculations, which can be a significant drain on memory and processing time. Again, we might have to face overfitting. With so many features, a model is at a high risk of learning the noise or random fluctuations in the training data, instead of the actual underlying patterns. This leads to a model that performs poorly on new, unseen data. Now let's have a look at dimensionality reduction. To combat the curse of dimensionality, we use dimensionality reduction techniques. These methods aim to transform the high-dimensional data into a lower-dimensional representation while preserving as much of the relevant information as possible. So what is feature selection? This involves selecting a subset of the most relevant features from the original set and discarding the rest. Also, let's have a look at feature extraction. This creates a completely new set of features by combining or projecting the original features. A popular example is principal component analysis, or PCA, which finds the directions or principal components where the data varies the most and projects the data onto these new axes. Even with the rise of vector embeddings, dimensionality reduction is still a crucial technique. While embedding models are designed to create efficient, dense representations, the resulting vectors often still have a high number of dimensions. Reducing these dimensions is necessary to address several ongoing challenges. First, the curse of dimensionality. Even in the context of learned embeddings, high-dimensional spaces can lead to problems. As the number of dimensions increases, the volume of the space grows exponentially, causing data points to become extremely sparse. This can make it difficult for algorithms to find meaningful patterns and can make distance metrics like cosine similarity less reliable. In essence, the high dimensionality can dilute the semantic signal the embedding was meant to capture. Second, the computational efficiency. High-dimensional vectors require significant computational resources for storage, processing, and retrieval. This is a major concern for real-time applications and large-scale systems. A 1024-dimensional embedding requires 4 times the storage space of a 256-dimensional one. For a database with millions or billions of vectors, this difference is substantial. The time it takes to compute the similarity between a query vector and all other vectors in a database increases with dimensionality. Reducing dimensions can dramatically speed up similarity search and make real-time applications like recommendation systems or semantic search more feasible. Third would be model performance and overfitting. While vector embeddings are designed to generalize, excessively high dimensions can still increase the risk of model overfitting to noise in the training data. Reducing dimensionality can simplify the representation, remove irrelevant information, and help the model generalize better to new unseen data. Fourth would be the visualization and interpretability. It's nearly impossible for humans to visualize data in spaces with more than 3 dimensions. By reducing the embeddings to 2 or 3 dimensions, we can use techniques like tsne or UMAP to create scatter plots that reveal hidden clusters, relationships, and the overall structure of the data, which is essential for understanding and debugging models. Vector indexing is a specialized data structure used to efficiently search and retrieve similar vectors from massive datasets. It is the core technology behind recommendation systems, image or video search, and large language models. In high-dimensional space, a brute force linear scan, which is comparing a query to every single item, is computationally expensive. As data grows, search time increases linearly. Vector indexing solves this by creating structures that enable approximate nearest neighbor searches, sacrificing 100% accuracy for massive gains in speed. So computers don't perceive meaning, they calculate it. Vector embeddings are numerical fingerprints that translate real-world objects like words, images, or audio into coordinates in a mathematical space. By mapping data this way, semantic similarity becomes spatial proximity. Concepts like cat and kitten aren't just related, they are literally neighbors in the vector landscape. While humans visualize in 3D, embeddings often exist in high-dimensional space with hundreds or thousands of x's. Each dimension represents a specific, often abstract feature of the data. The more dimensions available, the more nuance the model can capture about the object's identity. In a metric space, we move beyond intuition to calculation. We quantify how similar two objects are by measuring the mathematical distance between their vectors. So what is a distance metric? A distance metric is a mathematical formula used to measure the numerical gap or dissimilarity between two data points. In the context of AI and vector databases, it serves as a standardized ruler that determines how far apart two vectors are in a multidimensional space. While humans perceive similarity through meaning or appearance, a computer perceives similarity by calculating these distances. The smaller the distance, the more related the two objects are. First, let's talk about Euclidean distance. It is the length of the shortest path connecting two points in a multidimensional space. Think of it as a ruler measurement. It calculates the square root of the sum of square differences between coordinates. It is highly intuitive, but sensitive to the scale of your data. If one variable has a much larger range than others, it will dominate the distance calculation. Now you might ask what it is best for. So when the physical or numerical magnitude of the values matters equally across all dimensions. Next, cosine similarity. This is a measure of the orientation or angle between two vectors regardless of their size. Imagine two arrows starting from the same center point. Cosine similarity does not care how long the arrows are. It only cares about the angle between them. If they point in the exact same direction, the similarity is 1. It is best for text analysis and NLP. If two documents discuss Python programming, one might be 100 words and the other 5,000. Cosine similarity recognizes they are about the same topic even though their lengths or magnitudes are different. Third, we have dot product. So this is the sum of the products of the corresponding entries of two sequences of numbers. This combines both angle and magnitude. If two vectors point in the same direction and are very long, the dot product will be very high. It would be best used for recommendation systems. If a user likes action movies, which is the direction, and watches a lot of movies, which will be the magnitude, the dot product helps rank highly relevant popular items first. Fourth, we have the inner product, a mathematical generalization of the dot product used to define distance and angles in vector spaces. In most practical machine learning contexts like FICE or Pinecone, inner product and dot product are used interchangeably. It measures the projection of one vector onto another. Best for high-performance similarity searches where you want to reward intensity or frequency in the data. Fifth, we have the Manhattan distance, the sum of the absolute differences of their coordinates. Also called taxi cab distance, imagine a grid-like city like Manhattan. You can't walk through buildings in a straight line. You must follow the streets, horizontal and vertical steps. It is best for high-dimensional data or data with outliers because it does not square the differences unlike Euclidean, it is less likely to let one extreme value skew the entire distance. Sixth, we have the Hamming distance. The count of positions at which the corresponding symbols in two strings of equal length are different. This is used for categorical or binary data. If you have two strings like 1101 and 1001, the Hamming distance is 1 because only the second digit differs. Best for error detection in telecommunications, genetic sequencing, or comparing hashes of images to find near duplicates. Seventh, we have the J-card similarity. The size of the intersection divided by the size of the union of two sets. It measures overlap. If you have two shopping carts, J-card similarity looks at how many items are in both carts divided by the total unique items in either cart. It ignores how many of each item you bought. It only cares if the item exists in the set or not. Best for comparing sets of keywords, tags, or bag of words models. Eighth would be Minkowski distance, a generalized metric that acts as a formulaic framework for other distances. It uses a parameter p, where p equals to 1. When p is equal to 1, it becomes Manhattan distance, and when p is equals to 2, it becomes Euclidean distance. It is best for hyperparameter tuning. If you are not sure which metric works best, you can treat p as a variable and optimize it for your specific dataset. Ninth would be Chebyshev distance, the maximum absolute difference between any single dimension of two vectors. Also known as the chessboard distance. On a chessboard, a king can move one square in any direction, horizontal, vertical, or diagonal. The number of moves a king needs to reach a square is the Chebyshev distance. It only cares about the worst case difference among all dimensions. Best for logistics, warehouse routing, and cases where moving diagonally costs the same as moving straight. So moving on, vector indexing primarily focuses on approximate nearest neighbor search rather than exact nearest neighbor search. An exact search guarantees finding the absolute closest vector, but it's slow. ANN sacrifices perfect accuracy for significant speed improvements, which is often an acceptable trade-off for many applications. So you might ask how vector indexes work. In the world of approximate nearest neighbor search, almost every index follows one of these two structural philosophies, partition-based or graph-based. So first, let's talk about the partition-based indexing. The core idea here is to slice the vector space into distinct regions or clusters. When you search, the system identifies which region your query belongs to and ignores the rest of the map. So let's talk about IVF, Inverted File Index. This is the most famous partition-based type. It uses an algorithm like k-means to find centroids, which are central anchor points across your data. Every vector in your database is then assigned to its nearest centroid. Every vector in your database is then assigned to its nearest centroid, creating a cluster. Instead of checking every vector, the system finds the one or two centroids closest to your query. It then only scans the vectors inside those specific clusters. The subtypes would be IVF flat, which stores the full original vectors inside each cluster. It has higher accuracy but uses more memory. Then we have IVF/SQ or PQ. It stores compressed versions of vectors inside the clusters to save RAM. So It is best for massive datasets where memory efficiency is prioritized over raw speed. Second, let's talk about graph-based indexing. So instead of dividing the space into buckets, graph-based indexing treats every vector as a node and draws lines or edges between similar vectors. To find a neighbor, you walk through the graph. So HNS-W is the undisputed king of graph indexes, which stands for Hierarchical Navigable Small World. How it works: it builds a multi-layered graph. So we have the bottom layers and the upper layers. So the bottom layer contains every single vector with dense short-range connections, or we can call them the street map. And the upper layer contains only a subset of vectors with long-range connections. We can, as an example, treat them as the highway map. You start at the top layer. You make giant leaps across the database to get into the right neighborhood. Once you are close, you drop down to the lower, dense layers to find the exact nearest neighbors. It does not require a training phase like IVF. You can start adding data immediately. It is best for production environments where query speed and high recall are the top priority. Let's talk about dynamic indexing. A dynamic index is not a static data structure. It is an indexing strategy that allows a database to handle real-time changes like adding, deleting, or updating without going offline. So how it handles the live data? First, we have the buffer strategy. Most dynamic indexes use a buffer memory. When you insert a new vector, it isn't immediately woven into the complex HNS-W graph. It sits in a small flat index in RAM. During a search, the system queries both the main HNS-W index and this small buffer to ensure the most recent data is included. Second, we have the background merging. So periodically, the system takes the vectors from the buffer and integrates them into the main structure. Third would be automatic scaling. Some systems, like Waviate, start a collection as a flat index since it's fastest for small data. Once the collection hits a threshold, like 10,000 vectors, the system automatically promotes it to an HNS-W index in the background. Now you might ask about the key benefit. It prevents stale data. In older systems, you had to rebuild the entire index to see new data. Dynamic indexing makes new data searchable in milliseconds. So let's talk about compression. Compression is an optional layer applied to either of the above types to reduce the RAM footprint. The most common method is PQ, which stands for product quantization. So product quantization is lossy compression. It reduces a high-dimensional vector into a tiny code. It breaks the long vector into m smaller subvectors. For each subvector, it finds the nearest centroid from a pre-trained codebook and stores only the ID of that centroid. During search, the system uses these IDs to look up the approximate values in the codebook. You can reduce memory usage by up to 95%, allowing you to store billions of vectors on a single machine. Then we have scalar quantization, a simpler alternate to PQ. Instead of grouping dimensions, it simply changes the precision of the numbers. For example, converting 32-bit floats into 8-bit integers. The trade-off is that it's much faster to compute than PQ and loses less accuracy, but it only offers a 4x reduction in memory, whereas PQ can offer 10 to 50x. The semantic gap describes the fundamental challenge where the meaning or semantics of data Especially complex, unstructured data like text or images is lost or inaccessible when represented in traditional database structures. This gap explains why standard SQL and NoSQL databases struggle with similarity or semantic search in high-dimensional space, and why vector databases are superior for these tasks. The semantic gap is the divide between the raw data and its intended meaning or conceptual content. Now let's have a look at how traditional database represented our data. So first let's talk about SQL databases. So the data is stored in rigid tables, rows, and columns. Relationships are explicit, defined by keys and foreign keys. Search operates primarily on exact matching of string values or simple indexing of individual column properties. For example, finding all users where the city equals to London. Now, what was the failure point in this? If you search for a large domestic cat, a relational database cannot easily find records that contain big house feline because the system only knows the dictionary definitions of the words, not their contextual meaning or synonymous relationship. Now let's have a look at NoSQL databases. While offering more flexible schemata, they still treat data as discrete atomic units like key-value pairs, documents, etc. Search capabilities usually revolve around exact key matching or full text indexing or simple property filters. So what was the failure point in this? So for a query for like a holiday rental in Spain might pull up documents containing both words, but it won't be able to inherently rank a listing that says like let's say Spanish villa vacation stay higher than a listing that simply mentions Spain once in a completely different context. So in modern AI applications, data is often represented as vectors or array of numbers where each dimension captures a subtle semantic feature. A single vector might have hundreds or thousands of dimensions. So why did the traditional indexing fail? So traditional indexing methods like B-trees or hash maps are designed to handle low-dimensional data where ordering or equality are clear. They break down in high-dimensional space because, first of all, because of lack of ordering, because let's say in 1024 dimensions, there is no single meaningful order to efficiently compare the closeness of two vectors. And second would be the curse of dimensionality. As the number of dimensions increases, the volume of the space grows exponentially, and all data points become effectively equidistant from each other. This makes calculating the exact distance between every pair of vectors computationally impossible for large datasets during a search. So why vector databases are better? Vector databases bridge the semantic gap by fundamentally changing how data is stored, indexed, and searched. They treat data as high-dimensional vectors that encapsulate the data's true meaning. So vector databases store embeddings, numerical representations generated by machine learning models like BERT for text or ResNet for images. These models map semantically similar items to points that are closer together in the high-dimensional vector space. For example, the embedding for king will be much closer to queen than to apple. So in a semantic search, a query is first converted into a vector, or known as a query vector. The database then searches for the data vectors that are closest to the query vector using distance metrics like cosine similarity or Euclidean distance. The search directly finds items that are conceptually similar to the query, regardless of exact keyword matches. To overcome the curse of dimensionality, vector databases use specialized indexing techniques that enable fast, approximate search. So let's have a look at ANN algorithms, or also known as approximate nearest neighbor algorithms. So these algorithms sacrifice a tiny bit of search accuracy for massive gains in speed. They are crucial for searching billions of vectors in milliseconds. Popular examples include hierarchical navigable small worlds, also known as HNSW. This builds a graph structure where searches quickly navigate from close or far neighbors to find close neighbors. Then we have IVF, or inverted file index. This partitions the vector space into cells or clusters, allowing the search to skip vast areas of the space. A vector database is essentially built around three core pieces of information, often described collectively as a single data structure or record. Each entry or record in a vector database consists of three integrated parts: the vector, the unique ID, and the payload or the metadata. So first let's talk about the vector. So the vector is the mathematical heart of the record. In a database context, it is often called a point because it represents a specific coordinate in a multi-dimensional space. Data does not start as a vector. An embedding model like OpenAI's Text Embedding 3 Small or BERT acts as a translator. It takes unstructured data like a sentence, a JPG, or a WAV file and projects it into a coordinate system. A vector is an array of n dimensions. Each number represents a specific feature or latent trait of the data identified by the model, though these traits are usually not human readable. In a vector database, searching isn't looking for exact word matches. It's calculating the distance between points, like cosine similarity or Euclidean distance. High dimensionality allows for more nuance and detail in the data representation, but requires more memory and compute power to search. Then we have the unique ID. The unique ID is the immutable reference point for the record. While the vector is used for fuzzy searching, the ID is used for exact operations. For developers like you, the ID is the bridge between your vector store, like Pinecone or Milvius, and your primary relational database, like PostgreSQL. The database uses this ID to manage its internal inverted index. When the vector search engine finds the nearest neighbors, it returns a list of these IDs. If you need to update a record, like let's suppose the user edited their profile bio, you don't search for the vector. You target the unique ID to override the old vector with a newly generated embedding. Many databases allow you to partition IDs into namespaces or collections, ensuring that an ID is unique within its specific silo. And third, we have the payload or the metadata. So if the vector is the vibe of the data, the metadata is the fact sheet. This is structured data stored alongside the vector. It's usually stored as protobuf or JSON-B. This allows for flexible schemas where one record might have 3 fields and another might have 10. So advanced filtering or metadata filtering is where vector databases become truly powerful. So first, we have pre-filtering. The database first narrows down the records based on metadata, like where user ID would be equal to anything, and then performs the vector search on that subset. Then we have post-filtering. The database finds the top 100 most similar vectors and then removes any that don't match the metadata criteria. Modern systems use metadata to combine keyword search like BM25 with vector search. For example, you might want results that are semantically similar to LLM optimization, but also must contain the word Python. Metadata prevents hallucinations in RAG systems, which stands for Retrieval-Augmented Generation, by allowing the system to filter by source reliability, date, or access permissions. Hybrid search is where the real power of a modern vector database comes to life. as it leverages all three components we discussed: the vector, the ID, and the payload. Hybrid search is a technique that combines two primary search modalities to achieve highly accurate and relevant results. First, we have semantic search or vector search, which is based on the vector. And second, we have the keyword search or filtering, which is based on the payload or the metadata and the unique ID. First, let's talk about semantic search. This is the standard vector search process, which uses the vector component for relevance. Your query, for example, like movies about AI, is converted into a query vector using the same embedding model. The database then calculates the similarity, usually using cosine or dot product distance, between your query vector and all the stored vectors. It returns results that are semantically similar to your query, even if they don't share any of the exact same keywords. For example, a search for small furry animal companion might return documents containing the word cat or dog, even though those words were not in the query. The component used here is the vector. Second, we have keyword search. This leverages the unique ID and the payload or the metadata for precision and specific constraints. This further has two types. First is the filtering, and second is full text search. So first, let's talk about filtering. You use the structured payload or metadata to filter the results. You apply conditions to the non-vector data before or after the semantic search. This acts like the where clause in a SQL database. It ensures the returned results meet specific exact criteria. For example, you search for the semantic query above, like movies about AI, but filter the results to only include movies where the genre is sci-fi and the release year is greater than 2020. The component used here is the payload or the metadata for the filtering conditions and the unique ID to identify the records that pass the filter. Second, we have full text search. Some vector databases also integrate traditional full text or keyword search functionality directly. A separate search index checks for exact keyword matches or uses traditional inverted indexing techniques. It provides high precision when you know exactly what words or phrases you are looking for. For example, let's say searching for Lionel Messi will guarantee you find documents containing that exact name regardless of the document's semantic content. The component used here is often indexed fields within the payload or the metadata. Now, how do they combine? The hybrid approach uses a method called reciprocal rank fusion or RRF to combine the ranked lists from both the semantic search and the keyword search. The vector search returns documents ranked by semantic similarity score. The keyword search returns documents ranked by keyword relevance or simply selects a subset of documents. The hybrid search algorithm merges these two ranked lists into one final, highly relevant list, balancing conceptual meaning with specific constraints. This results in a search that is both contextually relevant, thanks to the vector, and factually precise, thanks to the payload. The embedding model is a crucial component in the overall function of a vector database, as it is the tool responsible for transforming complex, high-dimensional data like text, images, or audio into the numerical format that the database can store and query. This numerical format is called a vector embedding. the primary function of the embedding model is to map data from its original space, for example, the space of all possible English sentences, into a dense vector space. The embedding model acts as a translator. The model takes raw data, a block of text, an image file, a sound clip, or even structured data like a product catalog entry. It produces a list of floating point numbers known as a vector. This vector is the embedding. The length of this vector is fixed for a given model. This vector is a numerical fingerprint or dense representation of the input data. The key property is that the meaning or semantic content of the original data is captured in the vector's position within the vector space. Now let's talk about capturing the semantic meaning. This is the most critical function. The embedding model is trained in such a way that it places vectors with similar semantic meaning close to each other in the vector space, while vectors with different meanings are placed far apart. For example, the sentence, a large golden retriever is sleeping, will have a vector that is numerically closer to the vector for a big yellow dog is resting than it is to the vector for a rocket is launching into space. This proximity of meaning is what allows the vector database to perform semantic search. When you input a query, like healthy breakfast ideas, the database converts the query into a vector and then finds other vectors, like recipes, that are near it. Even if the recipe text does not contain the exact words, like healthy, breakfast, or ideas. The embedding models used today are typically deep learning models, often based on the transformer architecture like BERT, Roberta, or specialized models like SentenceBERT or OpenAI's text embedding models. These models are trained on massive datasets like the entire internet to learn the complex relationships between words, concepts, and ideas. A good model can generalize and produce high-quality embeddings for data it has never seen before, accurately capturing its novelty and meaning. The choice of embedding model directly dictates the quality and the performance of the vector database for a specific task. Now let's have a look at a few aspects and the impact of the embedding model. So first aspect is the search accuracy. A high-quality model improves both precision, the top results are exactly what you need, and recall, no relevant data is missed. Second, we have the storage and cost. The dimension count determines the storage footprint. Larger vectors require more RAM and disk space, increasing infrastructure costs. Third, we have inference latency, the time it takes to vectorize data. For real-time applications, a smaller, faster model like a bi-encoder is often preferred over a massive, slow one. And lastly, we have domain specificity. Models are not one-size-fits-all. A model trained on medical journals will fail at searching Python code because the underlying semantic relationships are different. So in summary, the embedding model is the intelligence layer that converts human understandable information into a machine-readable, semantically rich numerical format. The vector database then leverages this format to enable fast and accurate similarity search. Vector databases rely on measuring the similarity between high-dimensional vectors to perform effective search and retrieval. This is the core mechanism that allows them to find items that are semantically or numerically related to a given query. The concept of similarity in a vector database involves quantifying how close or alike two vector embeddings are. These embeddings are dense lists of numbers, often ranging from hundreds to thousands of dimensions, where each dimension represents some feature or characteristic of the original data. When using vectors from large language models, similarity often translates to semantic proximity. If two text passages are close in the vector space, it means they share similar meaning or context, even if they don't share many of the same keywords. In a high-dimensional space, our standard 2D or 3D intuition about distance can break down, a phenomena sometimes called the curse of dimensionality. This is why specific metrics are chosen to capture the most meaningful aspects of closeness for a given application. The choice of distance metric is crucial and depends heavily on the type of data and the specific problem being solved. The primary goal is to produce a score where a higher score typically indicates greater similarity, or in the case of distance, a lower score indicates greater similarity or closeness. So cosine similarity is the most widely used metric for tasks involving semantic search and natural language processing. It measures the cosine of the angle between two vectors, regardless of their magnitude. It focuses purely on the direction of the vectors. Based on the formula, as you can see, where A dot B is the dot product, and the norm of A and the norm of B are the magnitude of vectors A and B. The result is a value between -1 and 1. If it is 1, the vectors point in the exact same direction, which means highest similarity. If it's 0, the vectors are orthogonal, means no similarity. If it is -1, vectors point in diametrically opposite directions, which means highest dissimilarity. It is best for text embeddings, since text length or frequency can influence a vector's magnitude. Cosine similarity effectively normalizes this effect, ensuring that the semantic content is the primary factor in determining similarity. Euclidean distance, also known as the L2 norm, is the standard straight line distance. What it measures is basically the geometric straight line distance between the two vector points. We can see the formula, where d is the dimensionality of the vectors. The distance is a non-negative number. If it's 0, the vectors are identical, means maximum similarity or minimum distance. If we have higher values, the vectors are further apart, or minimum similarity or maximum distance. It is best for numeric closeness or non-sparse data where the magnitude of the vector, like the size of its components, and the absolute distance in the space are meaningful. This is often suitable for computer vision tasks like facial recognition, or purely numeric data where a short distance implies high closeness. The dot product is a measure of the scalar projection of one vector onto another. It measures the product of the vectors' magnitudes and the cosine of the angle between them. You can see the formula for this as well. The dot product is a direct similarity measure only if the vectors are normalized. If A and B are L2 normalized, the formula simplifies to A dot B equals to 1.1 dot cos theta, making it mathematically equivalent to cosine similarity. If the vectors are not normalized, the dot product favors vectors with larger magnitudes, even if their direction is less similar. This can be desirable in specific recommendation systems where the strength of the preference is a factor in addition to the item's features. The curse of dimensionality refers to the various counterintuitive phenomena and the computational challenges that arise when analyzing and organizing data in high-dimensional spaces. In a low-dimensional space, our geometric intuition about distance holds true. Objects clustered together are truly near each other, and the distance difference between the closest and the farthest neighbor of a given point is significant. However, as the number of dimensions increases, the ratio between the distance to the nearest neighbor and the distance to the farthest neighbor approaches 1. In other words, almost all data points become equidistant from a given query point. Imagine a sphere used for neighbor searching. In high dimensions, the volume of a hypersphere concentrates almost entirely in a thin shell near its surface, leaving the center mostly empty. This means most points are far out in the space, and the concept of nearness becomes ambiguous and less discriminatory. To maintain the same data density as you had in a 2D space, the number of data points needed grows exponentially with the dimension. High-dimensional spaces are incredibly sparse, meaning the distance between any two random points is likely very large, and the traditional metric of the distance does not reliably distinguish between a true nearest neighbor and an almost nearest neighbor. Since the distances between all points become very similar, standard distance metrics like Euclidean distance lose their effectiveness as discriminators for proximity, making it hard to reliably determine the true nearest neighbors. The most straightforward way to find the k nearest neighbors for a query vector is a brute force search or exact nearest neighbors. For a query vector Q, the algorithm calculates the distance between Q and every single vector in the database, and then selects the k vectors with the smallest distances. If there are n vectors and each vector has d dimensions, the complexity of a brute force search is O n dot d. As d increases, the time taken for each distance calculation increases linearly, which involves d subtractions, d squaring, and d additions. Since vector databases can contain millions or billions of vectors, the total time for n.b operations quickly becomes prohibitively long for real-time search applications. Even in indexing methods like KD trees, which work well in low dimensions, degenerate into brute force search in high dimensions because the number of possible partitions grows too fast, and points appear in too many partitions due to sparsity. To overcome the computational and geometric limitations imposed by the curse of dimensionality, vector databases transition from the quest for an exact nearest neighbor to using approximate nearest neighbor algorithms. ANN algorithms designed to find a vector ANN algorithms are designed to find a vector that is likely to be one of the nearest neighbors, accepting a small controlled loss in accuracy in exchange for a massive gain in query speed. As you can see the formula, Q is the query vector. For easier words, we can say V star is the true exact nearest neighbor. let's call the other V as V complement for easy understanding. V complement is the approximate nearest neighbor found by the ANN algorithm, and C is the approximation factor, usually slightly greater than 1. So vector databases are specialized indexing techniques. Use specialized indexing techniques to structure the high-dimensional vectors for fast lookups. We have tree-based methods in which data is partitioned hierarchically, but instead of using orthogonal cuts like in KD trees, they use random planes to divide the space. Search time is much faster than brute force, typically O log of n. Then we have graph-based methods. This is one of the most effective and popular methods. It builds a multi-layer graph structure where the bottom layer contains all data points and upper layers contain sparser shortcuts. Search starts at a high layer and rapidly traverses to the neighborhood in a lower layer. This is highly efficient and offers an excellent speed-accuracy trade-off. Then we have hashing-based methods. This technique hashes vectors into buckets such that vectors that are close in the high-dimensional space are mapped to the same or nearby buckets with a high probability. Search is then restricted only to vectors within those specific buckets, drastically reducing the number of distance calculations needed. By employing ANN algorithms, vector databases can perform similarity searches on billions of high-dimensional vectors in milliseconds, making them practical for applications like semantic search, large-scale recommendation systems, and image retrieval. While approximate nearest neighbors is the technology that powers the performance of vector databases, it's essential to understand exact nearest neighbors, as it represents the theoretical perfect benchmark for vector similarity search. ENN, also known as a brute force search, is the process of finding the true nearest neighbors to a query vector within a dataset. An ENN search guarantees that the results returned are mathematically the absolute closest vectors based on the defined distance metric like Euclidean or cosine distance in the entire dataset. By definition, ENN achieves a recall of 100%, meaning it never misses the closest neighbor. So how exact nearest neighbors work? The mechanism of ENN is straightforward but computationally demanding. The algorithm takes the query vector Q and sequentially iterates through every single data vector D in the entire dataset. For each data vector D, it calculates the precise distance between the query vector and the data vector. It maintains a running list of the k vectors with the smallest calculated distances found so far. Once every vector in the dataset has been checked, the algorithm returns the list of k vectors with the overall minimum distances. While ENN is perfectly accurate, its performance scales linearly with the size of the dataset. In a real-world vector database with millions or billions of high-dimensional vectors, the latency of ENN is measured in seconds or minutes, making it unsuitable for real-time applications. ANN sacrifices a bit, or should I say a tiny bit of recall to achieve millisecond latency, which is the fundamental reason it is the only viable approach to large-scale vector search. ANN is the foundation of modern vector databases. It solves the scalability problem of exact nearest neighbor search, where comparing a query vector to every single vector in a massive dataset is computationally infeasible. The core idea of ANN is to trade a slight loss in recall or accuracy for massive gains in latency or speed. So what is a recall or accuracy? Recall represents the probability that the query's true nearest neighbor is included within the set of approximate results. While exact nearest neighbor search guarantees a perfect recall of 100%, approximate nearest neighbor algorithms trade a slight drop in recall for significant gains in search speed. What is latency and speed then? This is the time taken to return the search results by avoiding a comprehensive comparison against every vector. ANN significantly reduces the number of distance calculations, leading to millisecond search times, which is critical for real-time applications. The trade-off is managed by tuning parameters specific to each indexing algorithm. Increasing these parameters generally improves recall, but increases latency and vice versa. These algorithms are data structures designed to quickly navigate and prune the search space of high-dimensional vectors. So first we have HNSW, which stands for Hierarchical Navigable Small World. HNSW is currently considered state-of-the-art for its excellent balance of speed and accuracy. It's a graph-based index where each vector is a node. The graph is constructed in multiple layers. So we have the top layers. This contain nodes with long-range connections enabling fast traversal over large distances. Then we have the bottom layers. These contain all vectors with short-range, fine-grained connections. A search starts at a random entry point in the top layer and uses greedy search to find the nearest neighbor in that layer. It then drops down to the next layer and repeats the process, effectively traversing the graph from large distances to fine-grained distances until it reaches the most accurate neighborhood in the bottom layer. Then we have IVF, also known as Inverted File Index. IVF works by partitioning the vector space into clusters, similar to how an inverted index works for text search. The index is built by running a clustering algorithm like k-means on the dataset to find n cluster centroids. Each vector is assigned to its nearest centroid. The index then stores for each centroid a list of all vectors belonging to its cluster. The query vector is first compared only against the n centroids to find the w closest centroids. The search is then restricted to only the inverted lists associated with these w closest centroids, drastically reducing the search space. Then let's talk about product quantization, also known as PQ. So PQ is a technique primarily used for vector compression to reduce the index's memory footprint and speed up distance calculations. It is often used in conjunction with other indexes like IVF. So a high-dimensional vector V is split into m smaller subvectors. For each subvector dimension, a separate clustering or quantization process is performed to create a small codebook. Instead of storing the full high-precision vector, the vector is replaced by a set of codes from the codebooks, one code for each subvector. This significantly reduces memory usage. Distances are calculated using the compressed codes. This involves looking up pre-computed tables of distances between the query subvectors and the codebook entries, which is much faster than calculating the Euclidean distance between full vectors. Then we have other hybrid methods like locality sensitive hashing or LSH. This uses hash functions to group vectors that are near each other into the same buckets. Search is restricted to the buckets the query vector falls into. It is generally simpler and faster to build than graph methods, but less accurate. Then we have disk ANN. This is basically an algorithm optimized for datasets that are too large to fit in memory. It uses principles similar to HNSW, but carefully organizes the graph structure for efficient disk access to minimize input-output overhead. So building and maintaining the ANN index is a continuous operation in a vector database. So now let's talk about how vectors are inserted, updated, and deleted. So when a new vector is inserted, it must be integrated into the index structure. For HNSW, the new vector is added as a node and connected to its neighbors across all relevant layers of the graph, which is computationally intensive. For IVF, the new vector is assigned to its nearest centroid, and its ID is added to the corresponding inverted list. This is generally faster than HNSW insertion. A vector update usually requires a delete followed by an insert of the new vector. Due to the complexity of modifying complex data structures like HNSW graphs on the fly, many databases handle updates by marking the old vector as deleted and inserting the new one. The actual removal of the deleted stale data is often handled by a background process. Deletion is typically a lazy operation. The vector's ID is merely marked as deleted or stale in a side structure, meaning it will be ignored during search. The physical removal happens during periodic index optimization or garbage collection to maintain performance and index size. The complexity of ANN indexing creates significant overhead compared to simple key value storage. The index structure itself consumes significant memory and disk space, often many times the size of the raw vectors. The initial construction can be time-consuming and computationally expensive, especially for billions of vectors. The cost of inserting, updating, and deleting vectors, as well as periodic background optimization, adds continuous overhead to the system. This overhead is the price paid for the low latency of ANN search. Retrieval models in the context of vector databases are the sophisticated systems and the algorithms that govern how relevant information is efficiently and accurately fetched from the database using vector embeddings. They are the core mechanism that enables semantic search, where the system searches based on the meaning or context of a query, rather than just exact keyword matches. In a vector database system, all data is first converted into high-dimensional numerical arrays called vector embeddings using an embedding model. Semantically similar items are mapped to vectors that are positioned closer together in the vector space. So the retrieval model's job is to first vectorize the query, which is to take the user's input and use the same embedding model to convert it into a query vector. Then similarity search. Quickly and efficiently search the vector database to find the stored data vectors that are the closest to the query vector. Third, return relevant data. So basically to return the associated original data for the top scoring closest vectors. The most common application for these retrieval models is in RAG system, also known as Retrieval-Augmented Generation, where they provide large language models with up-to-date external and domain-specific knowledge to improve the factual accuracy of their responses. Retrieval models rely on several key technologies and stages to execute an efficient similarity search. So to determine how close two vectors are, the retrieval model uses a mathematical distance or similarity metric. So let's talk about cosine similarity. This basically measures the cosine of the angle between two vectors. It is the most common metric, focusing on the direction of the vectors rather than their magnitude. A value closer to 1 indicates high similarity. Likewise, we can talk about Euclidean distance. This measures the straight line distance between 2 points in the space. A smaller distance indicates higher similarity. Since a brute force search is computationally infeasible for large databases, retrieval models use ANN algorithms to quickly find the approximate nearest neighbors. This trades a slight loss in perfect recall for massive speed gains. So common ANN algorithms include HLSW, which basically builds a multi-layered graph where each layer is a skip list that enables fast reversal from a random point to the nearest neighbor. It is one of the most popular and efficient methods. We can also talk about product quantization. This compresses the high-dimensional vectors into a shorter, more memory-efficient representation to speed up distance calculations. Then we can go for locality-sensitive hashing, or LSH. This divides the vector space into buckets so that vectors close to each other are likely to be hashed into the same bucket, thus limiting the search scope. So moving on. The overall strategy for fetching the documents is often categorized into different retrieval types. First, we have dense retrieval. This is the semantic search enabled by vector embeddings and similarity metrics. It excels at understanding conceptual meaning and user intent, even if the query uses different words than the stored data. Then we have sparse retrieval. This involves traditional keywords-based methods like BM25 that search for exact term matches. It's fast and precise for specific technical queries but lacks semantic understanding. And finally, we have hybrid retrieval. This powerful approach combines dense vector search and sparse search. The results from both methods are merged and often re-ranked to get the best of both worlds: contextual understanding and keyword precision. After the initial retrieval, advanced systems often employ a second stage to refine the results, called reranking. A second, more computationally intensive machine learning model, often a cross-encoder, is used on the smaller set of retrieved documents. This model performs a deeper, pairwise semantic comparison between the query and each document to reorder them, ensuring the most truly relevant documents are at the top. This significantly boosts the final retrieval accuracy. A re-ranking model, also often called a cross-encoder, is a specialized component in an information retrieval system, particularly those using vector databases for semantic search. Its core function is to improve the precision and relevance of the search results initially retrieved by the vector database. It operates as the second stage in a two-stage retrieval system. Vector search is incredibly fast and efficient for finding documents that are semantically similar to a query. However, the initial retrieval often prioritizes recall, which is finding a broad set of potentially relevant documents, and may sometimes miss the most contextually relevant result for a specific nuanced query. So let's talk about the first initial retrieval stage. So a user's query is converted into a query vector using an embedding model. The vector database performs a fast search, typically using approximate nearest neighbor algorithms and a distance metric like cosine similarity to quickly retrieve the top n documents whose vectors are closest to the query vector. This stage is highly efficient, enabling search over billions of documents, but the relevance ranking is based solely on the pre-computed static document vectors, which can sometimes result in information loss or a mismatch with the user's true intent. Then we have the second stage, which is reranking. The reranking model takes raw text of the original query and each of the top n candidate documents retrieved in the first stage. It performs a deep joint analysis of the query document pair to compute a more precise, contextualized relevance score for each pair. The documents are then reordered based on these new, more accurate scores, ensuring the most relevant items are pushed to the very top of the final list. Finally, only the absolute top results are passed to the end user or to a large language model in a Retrieval-Augmented Generation or RAG system. So, how re-ranking models work? Most modern re-ranking models are built on transformer architectures and are classified as cross-encoders, as opposed to the bi-encoders used for initial vector generation. So, what is joint encoding? Unlike a bi-encoder, which processes the query and document independently to create separate vectors, a cross-encoder takes the query and the document text concatenated together as a single input sentence. By processing them jointly, the cross-encoder can capture deeper semantic interactions and subtle relationships between the query terms and the document content. This allows it to evaluate relevance far more accurately than simple vector distances. The model outputs a single scalar score representing the probability or degree of relevance of that specific document to that specific query. This deep contextual analysis is computationally much heavier and slower than simple vector distance calculation. This is why re-ranking is only applied to a small subset of the initial results, providing high precision without sacrificing the overall speed and scalability of the vector search for the entire database. So what are the benefits of using these re-rankers? The integration of re-ranking models significantly enhances the performance of vector search applications. So we have improved precision. They ensure that the documents which are most relevant to the query's nuance and intent are at the very top. We have better handling of complex queries. So re-rankers are better at deciphering ambiguity, specific details, or complex constraints within the query that might be missed by the initial vector comparison. And we have optimized RAG context. So in RAG systems, re-ranking drastically improves the quality of the context provided to the LLM, leading to more accurate, contextually rich, and less hallucinated final answers, while also reducing the number of tokens sent to the large language model. So what is an encoder in NLP? In the context of deep learning and natural language processing, an encoder is a neural network component that converts raw input data like text into a compact fixed-size numerical representation called a vector embedding. Think of it as a translator that converts human-readable words into a language that a computer can understand and process mathematically, while preserving the original meaning. So we input raw text like a word, a sentence, or document. The encoder uses mechanisms like self-attention to analyze the context of the words and distill their meaning. So the output is a dense vector that mathematically represents the input's meaning. Semantically similar texts will have embeddings that are close together in the vector space. The encoder's job is to create a high-quality contextual summary of the text. The terms bi-encoder and cross-encoder refer to different ways these text encoders are used when you have two pieces of text, like a query and a document, and you need to determine their relationship, like similarity, relevance, or entailment. So first, let's talk about bi-encoder. Bi-encoder uses two independent encoders, often with tied weights, meaning they share the same internal parameters, to process the two inputs separately. So the relevance score is calculated by comparing the two resulting vectors using a similarity metric like cosine similarity or a dot product. The two texts never directly interact during the encoding phase. The only interaction happens at the very end, when their final embeddings are compared. The key advantage is speed and scalability. Document embeddings can be pre-computed offline and stored in a vector database. For a new query, you only need to encode the query once and then perform a fast nearest neighbor search against the stored document vectors. This is highly scalable for millions of documents. So the primary use case would be first stage retrieval or semantic search. Then let's talk about cross-encoder. Cross-encoder processes both input texts jointly in a single pass through a single encoder. The encoder itself outputs a direct relevance score between 0 and 1. The tokens from the query and the document interact directly within the encoder's self-attention mechanism at every layer. This allows for a much deeper, fine-grained analysis of their relationship. The key advantage here is accuracy and precision. The joint attention captures subtle interactions. For example, what is the capital of France? And Paris is the capital of France, which leads to superior accuracy. Primary use case would be reranking and high precision classification. The key disadvantage would be low scalability. Since every query document pair must be passed through the full model in real time to get a score, you cannot pre-compute scores for the entire corpus. This is computationally expensive and slow for large-scale retrieval. In most real-world applications, especially for semantic search engines and RAG systems, a hybrid approach is used to balance the speed of bi-encoders with the precision of cross-encoders. So basically, bi-encoders use the fast and scalable bi-encoders. Retrieval uses the fast and scalable bi-encoders to quickly scan millions of documents and retrieve the top 100 to 1,000 most promising candidates. So basically, we have high recall. And in terms of re-ranking, this uses high precision cross-encoder to score and re-rank only those 100 to 1,000 candidates, selecting the absolute best results, which in this case would be high precision. This two-stage pipeline provides an optimal trade-off between speed and accuracy. RAG is a technique that enhances the reliability and factual accuracy of large language models by giving them access to external, up-to-date, and private data sources beyond their original training set. The vector database is a critical component that sits between the user query and the large language model. The user's input query is first converted into a high-dimensional numerical vector, using the same embedding model that was used for the source data. This query vector is sent to the vector database. The database performs a similarity search to find the data vectors that are mathematically closest to the query vector. The database retrieves the original text chunks associated with the nearest vectors. This retrieved information is the context or knowledge snippet. The retrieved context is then packaged together with the original user query into a single comprehensive prompt. The LLM then uses this specific context to generate a factual, relevant, and grounded response, mitigating the result of hallucination. Vector databases are essential for grounding LLMs with private or external data. LLMs are powerful, but their knowledge is static and limited to their last training cutoff. Vector databases allow them to access dynamic, real-time, or proprietary information that was not in their training data. By providing the LLM with relevant, verifiable facts, the vector database forces the model to base its answer on external evidence, significantly improving the response's factual accuracy. Vector databases are optimized to store, index, and query unstructured data like text, images, and audio, converting them into searchable vectors. This makes vast, complex datasets immediately usable by a large language model. Now let's look at a few use cases of vector databases. So, vector databases are versatile and power many high-value applications beyond RAG. First, we have semantic search. So, these finds documents, articles, or records based on the meaning or intent of the query, not just exact keyword matches. So how it works is that the query and all documents are represented as vectors. A search finds documents whose vectors are semantically close to the query vector. For example, a search for large vehicles might successfully retrieve documents containing the word trucks or lorries. Then we have recommendation systems. They suggest items or users that are similar to what a user has interacted with or liked in the past. Items and users are vectorized based on features or past behavior. Finding a similar item means searching for items whose vectors are close in the vector space. Then we have image and multimodal search. This allows searching across different data types. For example, using a text query to find a relevant image or an image to find similar images. So how it works is that specialized multimodal embedding models map different data types into the same vector space. This allows a text query vector to be compared directly against an image vector to find semantic matches. Then we have anomaly detection. So these basically identify rare, suspicious, or outlying data points like fraudulent transactions or network intrusions. So how these works is that normal data points tend to form dense clusters in the vector space. An anomaly is a data vector that has a large distance from the average vector of its cluster or from all other vectors, indicating it is an outlier. Before data can be loaded and queried, it must be properly prepared. The embedding model is perhaps the most crucial step, as it determines the quality of your vector representation and ultimately the search accuracy. The model must be trained on data relevant to your use case. For example, a biomedical model for medical documents, or a general purpose model for common text. Models produce vectors of different lengths. Larger dimensions often capture more nuance, but increase storage and search time. Balance the model's accuracy against its speed and computational cost when generating embeddings for both the initial dataset and real-time queries. Let's talk about chunking and overlap. Since LLMs and embedding models have input limits, large documents must be split into manageable pieces. First, let's talk about chunking. The process of dividing a long document into smaller, self-contained sections is called chunks. The goal is to ensure each chunk contains enough context to be useful when retrieved, but is small enough to fit within the input limit of both the embedding model and the LLM prompt. Typical sizes range from a few hundred to a couple of thousand tokens. Then we have overlap. A small section of the previous chunk is included at the beginning of the current chunk. The goal is to prevent important information from being split across two chunks, ensuring the retrieved context is more coherent. Then let's talk about vectorization and loading. This is the final process of getting the data into a usable format within the vector database. The cleaned, prepared, and chunked data is fed into the pipeline. The chosen embedding model is used to transform each chunk or item into a high-dimensional vector. This vector is a numerical representation that mathematically captures the semantic content. The resulting vector is stored into the vector database. Importantly, the database also stores the original corresponding data, like the payload or the metadata, such as the original text chunk, a file path, a product ID, or a timestamp, which can be retrieved during the search phase. The vector database builds an efficient search index over the vectors to enable fast approximate nearest neighbor search for real-time retrieval. Vector databases use distance or similarity functions to measure the relationship between a query vector and a data vector. The function's result determines the retrieval ranking. The lower the distance, the more relevant the data vector is to the query. Let's talk about cosine similarity. This is arguably the most widely used metric for text and semantic search applications, including RAG. Cosine similarity measures the angle between two vectors, regardless of their magnitude. It focuses purely on the direction of the vectors. Why it's preferred for RAG? In text embeddings, the length of the vector often correlates with the frequency of the words in the original text, which can vary widely due to chunking. By ignoring magnitude, cosine similarity ensures that two documents with the same content but different lengths are still considered highly similar. It prioritizes the semantic meaning. The formula calculates the cosine of the angle between the two vectors. A score of 1 means identical direction or maximum similarity, 0 means orthogonality or no correlation, and -1 means opposite direction or maximum dissimilarity. Next, let's talk about Euclidean distance, also known as the L2 distance. This is the standard straight line distance you would measure in a geometric space. Euclidean distance measures the absolute physical distance between 2 points. It is often used when the magnitude of the vector is significant. This is common in metrics like computer vision or recommendation systems, where the size of the features is meaningful. If the data vectors are not normalized, Euclidean distance will be dominated by the magnitude. If the vectors are normalized, Euclidean distance and cosine similarity are mathematically equivalent. The square root of the sum of the square distance differences between corresponding components. A lower score indicates greater similarity. And lastly, we have the dot product. The dot product is the simplest form of vector comparison. It is the sum of the product of the corresponding components of the two vectors. If the vectors are normalized, the dot product is exactly equal to the cosine similarity. This is an efficient optimization used by many vector databases, as calculating the dot product is faster than the full cosine formula. If the vectors are not normalized, the dot product is a combination of both similarity and magnitude. A large score means greater similarity or relevance.